So today we are going to hopefully be able to kind of move on with the rest of section 19.1 in your notes. So on Friday we started out, we just had a really brief introduction to the definition of an acid and a base. And so on Friday we actually learned the Arrhenius definition of an acid and base, which was really the first kind of widely accepted definition for what makes something an acid versus then what makes something a base or basic. So the Arrhenius acids, we said they ionize or they break up in a solution to form H plus ions and something else. So we had a lot of our examples like hydrochloric acid, HCl, or sulfuric acid, H2SO4. They always had to have H plus. Bases, on the other hand, Arrhenius said that they would always ionize and yield OH minus or hydroxide, one of your polyatomic ions that's on your polyatomic ions table. So that included things like our most famous base, sodium hydroxide, NaOH, but it could also include any other hydroxide, so potassium hydroxide or calcium hydroxide or magnesium hydroxide. It included a lot of different chemicals as well, but they always had to have hydroxide in them. What we found, though, over time is this didn't really hold up. There were other things that were basic or kind of the opposite of acidic, could neutralize acids, that weren't necessarily always having to contain hydroxide, OH minus. You guys actually saw an example of this in your lab, but we'll kind of talk about that here in a second. All right, so the definition we're going to talk about today is one that's a lot more widely accepted, and it includes a lot more substances, so it's going to be a lot more useful for us to use this definition instead of just that most basic, that most kind of simplified definition of the Arrhenius one. The one we're going to talk about today is really going to be the best one. So we're going to spend the most time using this definition instead of the other one. But I think you'll see there's a lot of similarities. All right, so the definition we're doing today is the Bronsted-Lowry definition. It's again just named after the people who came up with it. So two different guys, Bronsted and Lowry. All right. And so they are going to kind of be showing us a little bit different kind of approach to acids and bases. Right? So we'll start out with acids. Acids, actually, you're going to recognize, are pretty similar to what the Arrhenius definition was. So instead of saying ionize to yield H+, it's going to say that we're a proton donor. So if you're an acid, you're going to be considered a proton donor, meaning you're donating a proton, which we learned on Friday is the same thing as H+. So that hydrogen ion is the same thing as just a single proton in most cases. So ionizing to yield H+, donating H+, it's kind of all the same thing. So acids, really, their definitions don't really change a whole lot with the Bronsted-Lowry. It just changes really and affects the bases, actually. All right, so then when we move to our definition of a base, all right, so what's the definition of a base? Well, if an acid is a proton donor, then the base is going to be a proton acceptor. All right, so if you're accepting a proton, or if you're accepting something, it means you're taking it in, you're bringing it in, it's part of your chemical formula now. So a base is going to be anything that accepts H+, or gains H+, or takes in H+. All right, we're going to see a lot of examples of this here in a second. But what you should notice then is that while the acid definition included anything that was said in the Arrhenius definition, the base definition includes the Arrhenius bases. So it still includes things like NaOH, still includes all of those hydroxides, but it allows us to get a little bit more diverse in terms of some other bases that we can also include. All right, one of the most famous ones, or the one that kind of spurned this whole definition, this new definition, is ammonia, which you guys actually tested in the lab, and maybe you guys don't remember it from a couple days ago before the weekend. But ammonia, just like the drain cleaner, which was NaOH, right? Ammonia was one of those that when you test it with phenolphthalein, it turned that bright, bright pink. So that told us that it was basic, but if you look at ammonia's chemical formula, there's no hydroxide in it. So normally we wouldn't have said this was a base. We might have even tried to guess that it was an acid because there was only hydrogen in it. But what we're going to find out is it is basic, and we can kind of use what we know now with this new definition to show why that is. Okay, so let's see our first example of a Bronsted-Lowry acid-base reaction. And our most famous acid, this is one we talked about on Friday, is hydrochloric acid, HCl. All right, so we're all very comfortable knowing that that is definitely an acid. It definitely is going to have H plus in it. All right, so our acid is HCl. If we add it to water, which normally it is, we can see that it's going to split up into its ions. It's going to split up into H plus and Cl minus. And we know from what we talked about on Friday that H plus almost always immediately bonds with water, immediately joins water, or is donated to water, and ends up joining it to make a polyatomic ion. So in the Bronsted-Lowry definition of an acid and base, while we have HCl being an acid and donating a proton, water is actually considered a base by accepting that proton. All right, and so then the products of that reaction are that hydronium ion, H3O+, and the leftover chloride ion, Cl-. Okay, so that was a reaction that used some things that you already knew. Let's look at now that most famous Bronsted-Lowry base that we were just talking about, ammonia, NH3. All right, so Bronsted-Lowry definition and your experimental data from the lab showed us that ammonia is a base. So let's look at what happens when it's dissolved in water. All right, if we add it to water, if NH3 is a base, that means it should be accepting H+, which means that automatically water has to be an acid in this case and donate the H+ to NH3. All right, so if we look at how water splits up, it's going to split up into H+ and OH-. All right, it's going to donate the H+ to NH3. When this happens, the two products that it forms are NH4+, which should look familiar to you guys. This is one of your polyatomic ions from your table. It's ammonium, all right? It's a polyatomic ion, ammonium, NH4+. And the other product it makes, or that's left over from water after it's donated its proton, the leftover product is OH-, that hydroxide ion. So that hydroxide ion is what's making that solution basic. That's what's making the phenolphthalein turn pink, and that's what makes ammonia basic when it's in water. What you should notice when you compare these two reactions to one another, so let's look at that first reaction we did with HCl in water, and then the second reaction where we had NH3 in water. All right, both of them are just aqueous solutions that happen to react differently with water. We call this ability that water specifically has of being able to act in one case like a base, and then in the other case it actually acted like an acid. It donated a proton in the second one, but it actually accepted a proton in the first one. We call this ability being either amphoteric or amphiprotic. They both mean the same thing. So you could either say amphoteric or amphiprotic. Means you can behave like an acid or a base. Water has this ability, but there are other substances as well that you'll see eventually also have that ability. All right, next we're going to look at an example of a diprotic acid. All right, so we saw an example with a monoprotic acid, HCl, but let's look at a diprotic one, because what's kind of important here is that we're not going to be doing just your normal double replacement reactions. This is a different type of reaction. We're not just going to be balancing charges so that everything's neutral. We're going to be just transferring protons. So one proton's going to go from one substance to the next. So in this example, we're going to use hydrosulfuric acid as our acid, H2S, and we're going to pretend it's reacting with a strong base, so something that has hydroxide in it, OH minus. Okay, and so we have our acid labeled and we have our base labeled, A for acid, B for base. All right, and we can see our acid, if we only let it give away one proton, so 1H plus, then if we take away that 1H plus, what's going to be left over is it's still going to have one hydrogen and the sulfur, right? But it's going to have a negative charge now. So it's going to be HS minus and HS minus and H plus will form H2S total, all right? So if we transfer that proton then to OH minus, all right, we know that H plus OH minus is going to yield water, H2O, and we're going to be left over with HS minus at the end. Okay, if we go on to step 2 then, what could happen, theoretically, all right, is maybe that water and that HS minus undergo yet another proton transfer. Okay, so step 2, we're still going to have HS minus as our base, okay, or I'm sorry, HS minus is going to be our acid, sorry about that. HS minus is going to be our acid because it still has that H plus, it still has one more left to give, and now we have water that's going to be our base. Okay, so HS minus is going to break up into that last H plus and S2 minus. Okay, so just like the sulfide ion, all right, and it's going to donate that H plus to water. So now this time, again, when water gets H plus, it's going to become that hydronium ion, H3O plus, and sulfide is left over, S2 minus. So you can kind of see what that looks like when you have 2 steps. All right, we're going to take this reaction one step further. So we saw step 1, we saw step 2. Now we're going to really quickly just look at the reverse reaction of step 2, because with some of these reactions, they aren't really favored or favorable in one direction versus the other. Sometimes they are, but they have a lot of tendencies to kind of, they can either go forward or backwards. So if we wrote the exact opposite of what we wrote in step 2, so if we wrote the products where the reactants are and the reactants where the products were, we would see what you have on your screen there. So we'd have H3O plus S2 minus yields HS minus plus H2O. And if you look at this reaction, it still has the transfer of a proton. All right, just this time it's going to be transferred in the opposite direction it was the first time. So before we had a transfer from HS minus, the acid, we had a transfer to H2O, the base, in step 2. All right, so we formed hydronium and S2 minus sulfide. All right, in this reverse reaction though, if it had flipped directions and gone backwards instead, we would have H3O plus, hydronium, would now be the acid. It'd be the one giving an H plus to sulfide, to S2 minus, the base, that it would accept it, and then you'd get the products to be HS minus and H2O. All right, so this can happen sometimes, and so for that reason, we actually can label both sides of the reaction. So now we're just going to kind of simplify so you can see how we kind of do that. All right, so we're going to rewrite step 2. All right, step 2, again, we're going to have HS minus as our acid, H2O as our base, but on the other side, since we could technically go backwards, like we showed in the reverse reaction, that in reverse, H3O plus acts like an acid. So we call it the conjugate acid in this case. And S2 minus can act like a base and accept protons, so we call it the conjugate base. All right, what you should notice is that the conjugate base is made from the original acid. So you start out with an acid like HS minus and you form a conjugate base. Same thing for the other one, all right? You start out with a base like H2O and you form the conjugate acid, hydronium. Okay, we're just going to kind of run through a few examples on how to do these conjugate acid, conjugate base pairings. All right, so you've seen a few examples of them. We just haven't labeled all of them as conjugate acid, conjugate base pairs. All right, so one of the ones we can see a lot of the times is water. All right, we're going to see water with its conjugate acid and with its conjugate base eventually. All right, but this is really similar to what your homework's going to look like tonight. So really pay attention to this part. Make sure you understand it. Okay, so you can see we can have something if we start out with a conjugate acid. All right, so if they tell us, okay, this is an acid, that means that it's going to donate H+. So if we're told water is an acid, it means it's going to donate H+, or give away H+. All right, so it's going to lose H+, and when it does that, it's going to form its conjugate base, which is going to be OH-, what's left over after you've lost H+. Okay, so H2O's conjugate base is OH-. All right, so try this next one on your own. You're going to get the conjugate acid is HSO4-. Okay, and I'm just going to like awkwardly not talk for a little bit, but try and see if you can figure out what will happen if you give up H+. If you lose H+, you're going to lose the hydrogen, but you're also going to you can think of it as losing a positive charge, or you're going to get more negative when you lose that H+. Okay, so take a few seconds, try this one on your own, and then we'll see how you do. All right, how'd you do? If you lost H+, you should be now have no hydrogens, so it should be SO4, and then since you lost that positive charge, you're now 2- instead of 1-. So HSO4- went from being just a -1 charge to now it's a -2 charge. So you're at SO4 2- for your conjugate base. Okay, now we're going to see it the opposite direction. So what if we start out knowing something's a base, and then we need to figure out what is its conjugate acid going to be? All right, if you start out as a base, like we know how water is what we call amphoteric, so we saw one example where it started like an acid. We also know it can behave like a base though. So if we are told it's a base, all right, bases accept protons, accept H+, they take in H+, so they're going to gain H+ instead. All right, so when they form their conjugate acid, it's going to be whatever the base is with an additional hydrogen and a positive charge, okay, or additional positive charge. So if you start out neutral like water, H2O gaining H+ is going to give you a conjugate acid of hydronium, H3O+. Okay, so now again, this next one, you guys are going to try it on your own. So you're going to start out with PO4 3-. This is a phosphate polyatomic ion. Pretend it's only going to gain 1 H+. All right, so you're not going to balance it and make it completely neutral. It might still have a charge. All right, so it's only going to gain 1 H+. What would its formula be for the conjugate acid? All right, I'm going to again pause, give you some time, see how you do. All right, how did you do? All right, if phosphate, PO4 3- gains an H+, it's going to gain a hydrogen, but it's also going to get one less negative charge. So instead of 3- now it's going to be 2-. So HPO4 2- is going to be the conjugate acid of that polyatomic ion. All right, again, it could keep gaining more and more H pluses, so we could have 2 more steps after this, but that's not what it's asking for. It's just asking if it gained 1 H+, what would you have? All right, so here's a quick look at your homework. This is what you're going to be passed out in just a second. They'll pass it out for you. So you're going to be doing this now for a bunch of different ions or neutral compounds. All right, and you're either going to be given the acid and you have to find the base, so you have to figure out what happens after it donates an H+, or you're going to be given the base and you have to figure out the acid, which is what happens after it gains H+. All right, there's an example of an equation that you can kind of use all of your other ones to follow. So you're going to start with the acid and it's going to yield H+ and your base. All right, so you just kind of follow that same example for all of them. And I know you'll do great. Good luck. Use the rest of the class time, work together, work by yourself, but make sure you get it done before tomorrow. All right, see you guys. Good luck. Bye.